Hello. So today I would like to go over the modified marching cubes algorithm, and to do so I will be using chapter 3 of Eric Langel's voxel-based terrain for real-time virtual simulations, also known as the Transvoxel paper. Just a note, I will not be going over the original marching cubes algorithm or the theory behind it and its inspiration or how it works. That is a very well documented subject. It's the adaptations and modifications to this algorithm that make it performant, which are a little less well known, so I'd like to go over those today. And the modified marching cubes algorithm is really just an adaptation to the original marching cubes algorithm that provides two key benefits. It builds in vertex reuse so that you can keep down on doubling data that is being generated. And it also avoids the ambiguous cases. And these are cases where you have two cells and there's potentially two different ways that they can be triangulated. And if the incorrect triangulation is chosen, there will be disjoint holes that appear in the mesh. So the modified marching cubes achieves these goals by using a new lookup table that uses preferred polarity. And this preferred polarity is what handles the ambiguous case. By splitting out 3 of the original 15 equivalence classes, there's now 18 equivalence classes that are used to assure that the mesh is complete and free of holes. The other of these goals, vertex reuse, is accomplished by leveraging aspects of the algorithm itself, as well as using a history buffer that tracks complete decks, and decks will be explained a little bit later. So now I'd like to give a quick overview of the implementation details, and then in the actual code I will go through these step by step and explain in a bit more depth what is going on. There's quite a few steps to this, so we will begin at surface extraction, where you will create storage for vertex reuse. Then you will loop over every sample in the n by m by h array, and with every loop over x, you're going to OR a reuse mask with 1. Every loop over y, you're going to OR a reuse mask with 2, and then AND it with 6. And then every loop over z, you're going to reset the reuse mask with 4. When making these loops, or these samples, when loading these samples, you are going to make a call to process cell, and this is really where the entirety of the marching cubes algorithm takes place. So inside process cell, you're going to find the potential reuse location in memory. You're going to set the corner value of this location to 0 by FFFF. The reason why you want to set the corner values to this is they are used later. You're going to make a call to load cell. From that load cell call, you're going to get an equivalence class. From that equivalence class, you're going to get some class data and geometry information. The geometry counts will determine if there is a triangulation, and if there is, you're going to extract the vertex count and the triangle count from the bits that make up the geometry counts variable. From there, you're going to look up in the vertex code array from the table using the prior class or case index. And then for every vertex given by the vertex count, or for every vertex that needs to be generated per vertex count, determine the current vertex code given by the index, determine the current corner samples given by the vertex code, calculate an interpolation parameter based on the distances of the corner samples, then determine if the interpolation parameter lies on the edge or corner of a cell. If the sample lies along the edge of a cell, going to extract the edge index and the delta code from the current vertex code. If the vertex code or the reuse mask is valid, a vertex is found for reuse. Else, a new vertex is created and, if allowed, stored for later. Then you're going to record the vertex index that was used or generated for the cell at the given index count. If the interpolation parameter was instead 0, meaning that one of the samples lies directly at the corner of a cell, we want to determine which of the corners is being evaluated. And then if the reuse code is valid, we want to reuse the preceding cell. If the reuse code was not valid, but the corner may be used later, we want to copy the reuse location in memory to write the new vertex to. And then should the reuse code not be valid, generate a new vertex. If reuse is permitted at this vertex, write to the recorded location. And then just like with edges, you will record the vertex index that was used or generated for the cell at the given vertex index. Once you have all of these vertices created, you will then process all of these vertices using the triangle count, and then this will give you the triangulation for the cell. To load the cell and get the case index, you'll begin at corner 0 or corner index 0. Store the sample value as the distance at the index, and then you're going to concatenate the sign of each sample as the bits of an 8-bit case index value. And the index corresponds to the bit location. So index 0 is bit 0, index 7 is bit 7. And then finally, sample voxel just returns the loaded sample in the m by h array. And this is the code right here. It's just a lookup into a multidimensional array. Okay, beginning with the overarching extraction method, here we can see the cell storage is created in a manner that provides just enough room for 2 decks worth of history. And in this case, a deck just means the complete collection of cells spanned along the xy plane for any constant z value. The reason why we need 2 is due to how the algorithm works. Because you sample every cell in a plane, when you go to sample the next plane directly above it, this is really only a half step through the cell, because essentially the tops of the preceding deck coincide with the bottoms of the current deck. So to fully process a cell with reuse, you need to store both steps through the cell. After we create the cell storage, we jump into the processing loop where we can see the reuse mask or the delta mask being built. After the first cell has been processed, it is now possible to reuse vertices from the preceding cell. This is true until every x has been processed, at which time the x bit is reset by ORing 1 and 2, and then ANDing that result with 6. This has the effect of resetting the x reuse ability for the first cell of the new y value temporarily until it has been processed, and then after that first cell has been processed, the x reuse is turned back on, and this is repeated for every x for every y in that z. Once we process the entire deck, the only reuse that is allowed is now on the z-axis because we have completely reset, so to speak. So you can't reuse any x and you can't reuse any y vertices, only z vertices. And this remains true again until the first cell for the corresponding axis has been processed, at which time the reuse is turned back on. And now we're going to get into the heart of the algorithm, which is processing the cell. So to determine what cell that we are going to be writing to for reuse information, we start by selecting the cell in the current deck, deck 0, where it's offset by I using j loops with n voxels per loop, and this is just a standard way to index multidimensional arrays. After we have the specific cell that we're going to be writing to, we set all of the corners to this number, and this is used when generating corner values to determine if a previous vertex was in fact generated. Now that we have the prep work done, we can begin the actual algorithm. The first thing to do is to load the case index, which is going to be given by the load cell function. Then after you have the case index, you can use it to look up the equivalence class that this cell belongs to. The equivalence class then can be used to look up the class data, which holds the geometric information for triangulating the cell. If the cell contains a triangulation, it's performed now. The vertex count and the triangle count for this cell are found by extracting the bottom byte, the high and low nibbles respectively, and a vertex count is gotten by reusing the case index from load cell. And the vertex and triangle count are gotten by extracting the bytes from geometry counts, the nibbles from geometry counts. Before actually processing the cell, you will create the delta mask or the reuse mask for edges, and I will be 100% honest, I'm not too sure why it looks like this, but the best I can do to explain is that since the y-axis spans 2 bits worth of numbers, that middle bit is duplicated using this very interesting bit manipulation. Later, when the reuse is used, or when this is reused by the delta code, my best guess is that the extracted bits from the V code that you'll see further down line up with the duplicated bits, but I haven't investigated this too much to figure it out. However, this is what you need to do to generate the reuse code or the reuse mask for edges. Then now that we have all the relevant information, we can attempt to triangulate the cell. We will generate each of the vertices as required by the vertex count. The vertex will be a combination of 2 samples, and to figure out which 2 samples we need, we look at the vertex code generated just before the delta mask. The current vertex index, this A value, can be used as an index into the vertex code to determine what the vertex samples belonging to the desired triangulation are. The corners are then extracted from bits 0 through 5 of the V code. Once the sample corners have been determined, the position offsets can be calculated by adding the ijk coordinates to their respective axis positions, and the corner sample is also added to the respective position. After the positions have been calculated, the interpolation parameter can be calculated, and this will perform a fixed point interpolation between the 2 samples. Should one of the samples not be 0, meaning that the sample does not lie directly on the surface, the sample is along an edge and is treated separately from corner cases. In the edge case, the edge index and delta codes are calculated to determine where storage occurs and if reuse should happen. If the delta code is valid, then so too is a reusable vertex, and it is found at this point. Should the delta code be invalid, then a new vertex is generated, and using the interpolation parameter, the position is placed somewhere between the corners. If the corner can be reused, it is stored now for later. Either a reused or newly generated vertex is recorded for the current cell at the given vertex index. On the other hand, if one of the Voxel samples was 0, so too ends up being the interpolation parameter. In this case, we need to find which corner of the cell the surface lies at. If the first corner sample was 0, then so was t, and this is used to determine easily which corner sample we're going to use. Similar to edges, now we generate information for reuse, but the reuse here is a little bit different. The delta code is determined simply by inverting the bits of the number, or the corner number, and then being checked against the reuse or delta mask. The other difference is the index address. It is possible that there is not a reusable vertex for this sample, and that this sample itself is not reusable, in which case, if index address remains a null pointer, only the vertex is generated and is not used for, or is not set for reuse. If the vertex address is valid, then a newly generated vertex index is written to for later reuse. Similar to edges, any newly generated or reused vertex is also recorded for the current cell at the given index. And then finally, after the determined number of vertices have been generated, using the triangle counts, the cell is then stitched together using vertex indices for the cell and triangulation data given by the class data's vertex index information that determines how generated vertices should line up for the cell. So now that we have looked at the main heart of the algorithm, I'd like to look at two auxiliary functions, load cell and get voxel. To load the cell and return the case index, this is similar to the traditional marching cubes algorithm, where the sign of each corner sample is indexed to the corresponding bit of an 8-bit value. Because the distances for these samples need to be recorded, you can just smash everything into a monstrosity like this, and when you load the voxel sample for a corner, its distance is simultaneously loaded as well and stored. After the distance has been stored, the sign of the voxel value is then determined and shifted by its appropriate bit index. And then if the sign of the voxel value is negative, by ANDing it with the hex values corresponding to that bit index, the 8 corners can be easily concatenated into the corresponding case index for this cell. Just a quick note before looking at the getVoxel function, the reason why LOD scale is used here instead of say 1 is that this function is currently set up to handle the level of detail parts of the Transvoxel algorithm. However, I'm only going over the modified marching cubes part of the paper at this time. For level of detail, you don't want to shrink voxel blocks because it just creates really small meshes. So instead you want to double or quadruple sampling rates. And at LOD 0, which is what we're currently looking at, the scale ends up just being 1, so everything works out as normal. But for the getVoxel function, it's very similar to what we saw with the cell storage. It's just an index into a 3D array. And before we look at the last part of code, let's go back to the implementation details, and this is how we actually implement the reuse. So you can see it's very similar across both cases. You calculate the index, calculate the delta codes, you find the reuse deck, then you find the reuse memory. Underneath these as well, I've also put little clips of what the structures are that are used throughout the various code that you've seen. Integer 3D is again just very similar to a 3D vector, just using int32s instead of floats. Cell storage is the struct that is used for the reuse history. And then triangle is just a struct that is used for putting together the vertices during the triangulation. And to finish off, let's end with the last two functions, and these are the functions which actually provide the reuse locations. Reuse edge and reuse vertex are very similar, with the only real difference being in how the reuse index is generated. For corners, the delta code is simply added into the corner index, and for edges, the delta code is added into the index per active axis and then multiplied by 3. For both corners and edges, the axis direction deltas dx, dy, and dz are all similarly the active bits of the delta code, and the deck to be reused from is always determined by the dz code. After indexing the desired deck using the delta values as the reuse index, the previously generated vertex can be returned by moving back 1 from the corner index and moving back 3 from the edge index. Alrighty, now that all of that has been said and done, it is time to go ahead and actually run the code and show you the results of the extraction. And then sure enough, here we have a completely extracted triangle mesh. Now there is no texturing at the moment, it is only the mesh itself. All of that will come later in Chapter 5 of the Transvoxel paper, texturing and trilinear interpolation. However, to come next is level of detail. So stay tuned. So before I end the video, there's two things I'd like to talk about, and the first is about degenerate triangles. Using this algorithm, it is possible to create a triangle who has 0 area. The paper talks about using the fixed point interpolation parameter to check this. I couldn't quite get that to work, so instead I check the magnitude squared of the normal of the triangle. So if you treat the triangle as sitting directly on the face of a plane, you can calculate from a minus b and then a minus c, well really any of the combination here. You just need to use a consistent first vertex. But by generating the two directions of the triangle and then crossing them, you can get the normal of the triangle. And then by checking the magnitude squared of that triangle, should it not be 0, it was in fact a degenerate triangle, or the triangle has some surface area or area. The triangles that get thrown out, you just end up remapping, and I choose to do this validation process after the entire mesh has been extracted. The second thing I'd like to talk about is the lookup tables. The majority of what I showed you is using the lookup tables from transvoxel.org. The only difference is the regular vertex data. This is not the table that was used in the video. It was instead an updated table, also from Eric, that is found at this website, and it comes from the Foundations of Game Engine Development Volume 2 book, which is where the modified marching cubes that you saw today was also listed. So you can use the regular Transvoxel lookup tables, just replace the regular vertex data with the vertex code table here, and then everything will work out fine. Thank you all for your time, and I hope you are able to use this in your projects or just learn something from it.